My supervisors, Dr. Yasmin Arafa and Professor Cornelia. So I would like to talk today about my PhD research, which focuses on medical image processing and classification, particularly on diabetic retinopathy classification using deep learning. So the outline of my talk, today I will be taking you through a brief overview on the topic and the disease, and then the research aim of my PhD research, and then some remarks, conclusions from literature review, and afterwards the proposed deep learning model for this problem, and as well as the results that we have got so far, and finally the conclusions. Okay, so first of all, I'm not sure if anyone is from a medical background, but I think it would be useful if I just talk briefly about the disease itself. So diabetic, as you know, diabetes is like many other diseases. When it gets developed, it will have some complications. One of these complications, it's called diabetic retinopathy. It's a condition that occurs in the human eye, to be more precise, on the retina of the eye, due to diabetes mellitus. And diabetic retinopathy is a very common eye disease in diabetic patients worldwide, and it happens when the retina get damaged because of some changes of the blood vessels of the retina, some fluid leakage, or swelling, or bleeding, or growing some blood vessels, abnormal blood vessels. And if the disease left untreated or undiagnosed at an early stage, that will cause, it might cause blindness or loss of vision, if it's not treated at an early stage. Statistically, according to the World Health Organization, the number of diabetic adults in 2014 was approximately 425 million worldwide, and almost all patients that have type 1 diabetes mellitus, and more than 60% of diabetic patients with type 2 will develop diabetic retinopathy within the first 20 years of the diagnosis of their diabetes mellitus. So as I mentioned, it might lead to blindness. So to prevent this, the loss of vision for the diabetic patients from occurring because of diabetic retinopathy, the best modality is to diagnose it at an early stages. Nowadays, there's a different techniques and methods that ophthalmologists they use to analyze and diagnose the patients using fundus images that capture the retina of the eye, which requires the patient to do a regular screening yearly, or maybe several times per year. So however, this the ophthalmologists, they will need to look into this, capture the retina image and look into it and analyze it and diagnose if they have disease or they don't have it, and if they have it, what is the severity level of the diabetic retinopathy. But the problem with this is still we have some problem, especially in the undeveloped countries. It is still labor expensive, requires expert ophthalmologists to read and analyze and diagnose the images, and also it takes time. So therefore, automated image analysis of fundus images, we can benefit from the machine learning, the power of machine learning and AI techniques to automate this process that can act as a decision support system for the ophthalmologist. It can act support system for some early career ophthalmologist or non-expert, maybe anyone with medical part that will speed up the process. Here in this slide, I would like to show you just quickly. This is a normal eye, a normal retina of an anatomical part of the normal eye with a normal healthy parts, and the top one, and the bottom one is a diabetic retinopathy fundus photograph. As you can see, there are some spots, like red spots here, and yellow spots, and some other signs and lesions. Those are like blood leakage, and those things, when they develop, they will lead to blindness. So let's come to the our part, the machine learning or AI part. So in my PhD research, the major aim of the proposed research is to contribute towards improving the diagnosis of diabetic retinopathy by implementing a deep learning model for early detection and classification of diabetic retinopathy, that it is possibly more accurate than the existing published work. Since this area of research has been very active in the recent years. So after conducting a comprehensive literature review, here are some a few remarks I would like to conclude. So most of the studies in the field of diabetic retinopathy, the field of detection and declassification, they use a small data set, and they report a very good performance measurements results, and it has a very motivating and potential applications. But the problem with them, when you test it on another data sets, sometimes or many of the times they don't they have report they give you a poor performance because of the model is not well trained on a different formats of different kinds of images that taken from different cameras, different ethnicities, different qualities. So that's why a larger data set taken from different cameras and from different machines, and it has different ethnicities. The issue is that we want to address the problem as all, not only on this, to be biased to this small data set. Another thing is many papers or work has focused only on a particular diabetic retinopathy sign. One of those signs, for example, the red one or the yellow one I showed you, the hemorrhages and the exudates. And this is a decision support system. It helps in diagnosing, but it's still not very comprehensive for diagnosing and analyzing the images. So we need a more comprehensive system. One more thing is one of the challenges of the fundus images. The fundus image is the image that taken from the machine for the retina, is that the fundus images, that its most parts of the retina images are irrelevant to the diabetic retinopathy, to the disease, while some other parts of the input image have more, let's say, influences on the final label of an image. So the problem here comes that most of the convolutional neural network that approaches that they are proposed and employed for DR classification process the input data without considering this fact. So to address this problem in our my research, we have proposed to use something called multi-scale attention network to classify the diabetic retinopathy images that has a multi-scale attention mechanism to encode more local information from the representation of the image. So I want to here is as you can see is the proposed deep learning model in our research. It consists of different layers like any other model. So obviously the first thing we feed the pre-processed image in the first part here into an encoder to represent it in a different levels. In our model here, we have used the encoder, the ResNet, as an encoder. So it generates, as you can see here, the layers, a low level, mid level, and high level representations. And most of the research and many of the research and also the baseline models just connect the high level representation with the dense layer or the fully connected layer to generate the final output. In our case here, we have added a different more layers and more steps that improve the performance of the model, which is first thing is we combine all the low level, high level, and mid level representation together. We scale them and put them together to generate a multi-level representation, as shown here in the semantic learning, to generate the multi-level representation. And then on top of that, we use the idea of atrous convolution. The atrous convolution is it applies convolutional filters with different fields of view sizes, and that will help the network to let's say localize or encode more local information, semantic and local information. So after applying the utterance on top of the multi-level representation, the utterance convolution will generate information with different scales, and those scales can be combined to generate a multi-scale representation. So we use the multi-level representation first from the encoder, and then we use the multi-scale representation, and then we use the idea of the attention mechanism by creating an attention map, which is kind of a series of convolution layers applied to the multi-scale representation that we had here. So if we apply the attention mechanism to generate attention map and then multiply it, once we multiply it with multi-scale representation, with this representation, it will scale the representation again and give us the importance of the representation. So it will give importance to each representation to generate the final scaled representation. And after this step, we can, as any typical neural network, we connected with a Foley we do apply the global average pooling, and then and also the dense connected with the Foley connected layer to generate the final output here. In our case, the main objective of the model is to classify or categorize the images into classes based on the severity level of the eye. So if it doesn't have the retinopathy, if it's healthy image, or if it's not, and if it's not, what are the classes? So we've got 5 classes represented. I will come to this now, but it's from 0 to 4 classes. But we have also trained the model to discriminate between the healthy and unhealthy images as an auxiliary task, like to make the final decision for out of the 5 classes. Yeah, I think that's pretty much I wanted to say about the architecture. So in the results, for our final results here, the experimental results, first, the data set that we have used, they are 2 public open access data sets. It's called IPAX and Aptos. They are large data set, and you can access it from Kaggle. The first one, IPAX, contains around 33,500 retina images, and the Aptos consists of a total of 3,600, around 600 retina images. The image you see in this slide, it is actually a sample of retina images for different classes. So every class here, every image represents a different class based on the severity level. So for the model, 0 represent a healthy image, no diabetic retinopathy. 1 is a mild, 2 is a moderate, severe, and so on. So there are 5 classes. So the results, I'm not sure of the time, I've got time. So yeah, so the results, I'll go through the results quickly. So as I mentioned, we have created we experimented the model on multi-classes and binary classification for the same data sets. We used settings that other published paper they have already used the same data sets, and the 10% of the data is testing, and the rest is remainder is training. So as you can see, the result outperformed the state of the art for the very recent papers on these data sets, with 84 more than 84 accuracy and 91 sensitivity and specificity. And on the right side is the confusion matrix, is an accuracy for each class. Again, this is the binary, if it's healthy or unhealthy. Also, it performed really well, the model, also comparing to the baseline models. The other literature or papers, they have not reported the binary classification, so they are not included here. For the other data set, there's a recent paper. They have used a different approach. We use the same setting. They have used the same data set and settings, but with our method, it also outperformed in terms of the kappa score, and they have not reported also accuracy and other performance measurements. Here is also the confusion matrix for every class. Same thing for the binary. It's actually showing a really I think it's a good performance, and it is could be like a great clinical. I think it's a good clinical. It has a potential clinical application in the futures if it's applied as a whole vision support system. And one final thing in our evaluation was an ablation study, which is we removed some components of the model, of the developed model, to check how effective those components, which is I mentioned in my architecture, which is the multi-level and multi-scale representations. So you can see the difference in the accuracy with and without for both data sets. There is like a good difference improvement after using these approaches, and also for the kappa score. So also the kappa score is very important to check that the model doesn't have biasness in terms, because like for example the Aptus data, they are very imbalanced data in terms of the classes. The one class has like maybe 50% of the data set. So the kappa score is very effective or important to check the reliability on this model. Here is an example of how it looks like the attention map, which actually the attention mechanism, it helps the model to focus on the damaged areas to encode more local information to make the final decision and what is the areas that are affecting it. So as you can see for different classes, this is for class 0 and this is for class the moderate one, class 3. I think this is yeah, in the conclusion, as it is just the contribution that we have used the multi-level feature encoding structure, also the multi-scale attention mechanism. The performance has been improved by using the multitask learning, using the auxiliary task in parallel with the multi-class learning training. So also the binary classification training was helpful for the binary decisions. And the model has achieved like a good performance comparing to the literature review on 2 public data sets, which coming from a different image, from different machines and from different countries and different qualities and sizes. I think this is pretty much everything I wanted to say. But if you are interested to know, obviously, if you have any questions, you can post it. And if you are interested to know more, this work has been published in the IEEE Access, it's an open access journal as well. It's recently has been published in March. And yeah, that's everything I want to say. Thank you very much for your attention indeed.
Well, thank you very much for your talk. Could you maybe say a little bit about the importance of open access, source, and so on for your work? Maybe I have missed the piece, but I think it's sounded very important.
Yes, yeah. So, yeah, obviously, especially the medical data set is very, very difficult to have to get this data set from anyone to test your model and evaluate it. Without the open access data set that I found on Kaggle, I wouldn't be able to evaluate my model effectively and check how reliable it is, because of several data sets they are open access there. And the process of getting a data set from private places is very expensive, and it's very like a long process, especially for the medical parts. So yeah, I would say like it's the main, it's a core thing in my PhD is the open access for the data sets particularly.